Hi, I'm Larson. In this video, I will provide a short overview of a Nerf Sentry gun that was made for Michigan's EECS 373 class by Wesley Howell, Kenny Pryczynski, Samantha Silveira, and myself. Our Sentry gun design was made to provide an automated way of defending an area during a Nerf gun fight. The current implementation is made for automatically following a target and then shooting it once it is stationary. In the event that the targeting system is disrupted in some way, the Sentry gun comes with a manual override to allow continued operation. The Sentry gun consists of three major parts: the target tracking algorithm, the Sentry gun controller, and the physical Sentry gun itself. The target tracking algorithm is a MATLAB program that is run on a control computer. The gun controller is a Smart Fusion FPGA made by Microsemi. The Sentry gun is a Nerf Strife gun mounted on several metal plates, which is actuated and fired by several DC motors. Instead of a more traditional compressed air, the Strife uses flywheels to fire the Nerf darts. To use the system, you only need to run the MATLAB program on the control computer, and the Sentry will begin to track any faces that are in range. After a target has been locked onto for a few seconds, the gun warms up and begins firing at the target. The targeting algorithm is based off a computer vision system that is built into MATLAB. The control computer is connected to a webcam that is mounted on the Sentry gun. The system will lock onto the first face to enter the view of the webcam and report the coordinates of the face within the frame. We take these coordinates and determine if they are within a certain distance of the frame center. If they are not, the control computer sends the gun controller a message over UART telling the controller to aim up, down, left, or right. If the target is near the center of the frame, the control computer instead sends out an instruction to begin warming up the gun to fire. Once the target has been centered for a specified number of frames, the control computer sends the instruction to begin firing at the target. If the user chooses, he or she is able to disable the tracking algorithm and instead use the keyboard to control the Nerf gun. The Sentry controller has a Smart Fusion FPGA as its primary controller. The controller picks up instructions from the control computer off of UART and parses them into usable controls. The flywheels used by the Nerf gun to fire the darts are powered by the battery inside of the Nerf gun and activated by using a normally open relay controlled using GPIO. An ultrasonic sensor is used to determine the distance from the target. The ultrasonic sensor uses PWM as a control signal and returns a variable width pulse that corresponds to the distance from the target. A series of timers are used to calculate the size of the return pulses. 3 H-bridges are used to control each of the DC motors on the turret. The H-bridges are controlled by the Smart Fusion using GPIO pins and switch voltage from a 7.2 volt battery. In order to prevent stall damage to the DC motors at the extremes of the targeting area, shunt resistors are included in line with the H-bridges. The voltage drop across the shunts is read by an ADC and then used to calculate the current being used by the DC motors. If the current reaches the stall point, the Smart Fusion prevents continued movement in the direction of the motor it was going when it was stalled. The turret itself is actuated by 2 DC motors, one for horizontal motion and one for vertical motion. Gears are used to transfer the rotation of the motor to the desired axis of motion. A third motor is used to fire the gun. The motor rotates a gear that has approximately 80% of the teeth taken off. When the teeth of the motor gear catch the firing gear, a Nerf dart is pushed into the flywheels and fired. Once the motor gear passes the tooth section of its rotation, the firing gear is reset by a rubber band. Our design has issues with precisely tracking targets as it has a tendency to overshoot targets at certain points within its firing range. The gun moves between 2 locations on either side of the target because the DC motors move too quickly for the tracking algorithm to keep up. One way to slow the gun is to lower the motor voltages, but the issue then becomes that the turret cannot move in certain ranges of its motion due to not having enough power. With time, we could modify the targeting system to have a faster tracking rate, and the motors to move in a predetermined steps that would be accounted for while tracking. A second issue with our designs is using shunts to accurately detect motor stalling. Because the loads on the motors vary depending on the current position of the gun, the current under normal operation varies over a range of about half an amp. Due to the low operating voltage of the motors, the stall current is only about 200 to 300 milliamps above the average operating current. At the extremes of the Sentry's aiming range, this difference decreases to be too small to reliably detect. As a result, the gun would sometimes become unresponsive. If given more time, we could have implemented a filter to the current readings to better detect stalls. Overall, our Sentry gun project worked quite well over the majority of the targeting range. Targets were tracked and shot reliably, issues only arising near the limits of our setup.